Swayam Prabha. Digital India. Educated India.
Okay, good morning. So last class we discussed about cache and we saw this algorithm that I have put on the screen, whatever I have written in red. So the CPU actually generates the address, right? It gets converted into an effective address. So it generates a logical address, it gets converted into an effective address. For the current class, let us assume that there is no paging. So it generates an address and then this address is input into the cache memory, and if this address is available in the cache, we go and fetch it. This is called a cache hit. If the address is not available in the cache, then we go and fetch it from the RAM, put it into the cache and then consume it, then it is called a cache miss. And how do we go and check whether a particular address is there in the cache or not? We gave a very simple example of a 6-bit memory, whatever I am marking here. Let me use the green pen here. So in which and I have a 2-bit 4 location cache. So I use the last 2 bits to index into that location, and the first 4 bits as tag bits, as you see here. Okay. I am marking in red. The first 4 bits as tag bit, the last 2 bits are used to index into the location, and then there is a valid bit and an invalid a valid bit and a dirty bit for obvious reasons. We have discussed this in the last class, and every instruction set architecture, again I am marking in red here on your right hand top, has an instruction called invalidate cache, which will go and make the valid bit 0. So when I generate an address in this context, I take the last 2 bits and index into this location. If I find the valid bit to be 0, then it is a cache miss. If I find the first, that if the valid bit is 1, then some address is stored there. I take the first 4 bits, namely B2 to B5, and compare with the tag. If they match, then it is a cache hit, otherwise it is a cache miss, right. So this is how caches basically work. Now let us go and enhance this idea. So this is called a directly mapped cache or direct mapped cache, because there is nothing that I am translating here. I am just taking the direct address that is generated by the CPU, just using 2 bits and directly mapping it onto the cache. One of the serious disadvantage of this is that there is a lot of collisions, right. Collision in the sense 0, 4, 8, 12, 16, all these addresses collide, they are all stored in the same, if at all they are going to be stored in the cache, they should be stored in 0th location. So when 0 is there, I want to now access 4, 0 has to be taken out and 4 has to be put there. This is called collision, right. So in data structure course you would have learned hash function, right, and collision. This is a very trivial case of hashing. We can't do any, we don't want to do anything more than this, because it is done at an instruction level. I don't want a Montgomery hash function to sit there, okay. I want to have a very simple mapping mechanism. I don't want a very complex mechanism, because it will hit what? It will hit the timing performance. Your instruction execution or your throughput, number of instructions per clock cycle, will go down, right, and that is why I would like to have a very simple hash function to start with. Are you able to follow? Okay. Now let us go to the next part. Let us see what is advanced in this. Okay. Now as you see here in the 0th location, 0, 4, 8, 12, so many addresses mapped on to 0, so many on to 1, so many on to 2 and so many on to 3, okay. And what happened if 0 is stored, now 4 has to be stored immediately, I have to replace 4. Instead what I will have is, instead of one set of locations, let me have a pair of locations. So these addresses, the 0, 4, 8, 12 can be either stored here or it can be stored here, right. Similarly 1, 5, 9, 13 can be either stored here or here, here or here, here or here. So this is called a two-way cache. How do you know, how do you implement it? Okay. So I take 0, suppose I take some address, let us say it is mapped on to this location, let us say some 16, 16 gets mapped on to this, if at all 16 is stored, it should be stored either here or it should be stored either here. So I know which line, so I told you right last class, this is called a cache line, right. I know which line this address could be stored, if at all it is stored. I go to that line and ask, array, is this address stored in your line? That means I am querying two memory locations concurrently and asking a question, is this tag bit, right, is the tag bit of, say, let us say 16, so what would be, so 2 bits, right, 16 is what, 1 0 0 0, let us say, right, this is 16, right, yes or no. So this is stored in location 0. So I will go and ask, is 0 1 0 0 stored as a tag in either this in this location or in this location. What do you mean by stored? The valid bit should be 1 and the tag should be 0 1 0 0. I am asking this question. So in the past you have seen several memories, where do you ask such type of a question? If I ask such type of a question, what is that memory called? Content addressable memory or associative memory. Now each line here should be implemented as an associative memory. So I index into that line like a normal memory, because I take these two 0 bits and say I have to go and look into this location. The last 2 bits in this case point to that location. So it is like a normal memory there. After I get that line, in that line there are several sets, several versions of this memory. So I go and ask these fellows, hey, is my tag stored there? Is the valid bit 1 and my tag is stored? So there what I am asking whether a content, I am giving the content and asking whether that content is stored there. So horizontally this memory is implemented as a content addressable memory, vertically it is a normal memory. So each of these is called a way, right. So this is two-way, and since it is an associative memory, it is not a fully associative memory, it is associative on each of these, we call it sets, okay. So this is a two-way set associative cache. Okay, this is a two-way set associative cache. Modern processors will have something like four-way set associative cache. Four-way set associative. So I will have 4 such versions of this memory. So a particular address can either be stored here or here or here or here, right. In one of these caches it can be stored. Right. If all the, suppose I have two-way set of cache, 0 is occupied here, 0 sits here, and say some 8 sits here, and say some 16 sits here. Now I want access 4, then within this cache line I have to do some replacement algorithm. It can be least recently used, I told you, right, LRU. least recently used or such algorithms. I will cover one such algorithm in the class, okay, as an implementation. Lot more details can be taken up in a advanced architecture course, but at least here I will cover how to implement in hardware one such class replacement algorithm. I will take the most recent one followed by the modern Intel and AMD processors, okay, and I will teach you like so nevertheless today, so 8 and 16 are stored in that line. Now 0 wants to come, 0 has to stay in one of these fellows. Instead of just 1, now I have made it 2. So now between 8 and 16 I have to decide whom to move, right. So the hardware has to make, now this is no software business, this is not operating system business. The hardware has to make a choice between whom to move. Should I move 0 or should I move out 8 or should I move out 16? So there are lot of ways by which the hardware can decide, that is called a cache replacement policy. So the hardware has a policy based on which it decides whether I should move 8 out or 16 out to accommodate say 4. Right. So this is the notion of a 4-way set associative cache, and why I have a 4-way set, so all the modern processors to the best of our knowledge they do not reveal the architecture. So Intel latest processor, what is the cache, we do not know, they do not reveal it, but intuitively we see that it is basically a 4-way set associative cache, it is not more than 4-way, okay. Now what can drive your intuition for this? Suppose you are given this problem of saying decide the number of ways in your set associative cache. How will you come out with that? How will you answer this question? To be more specific, a 5-way will not yield any benefit, it may yield some very minuscule benefit. Beyond 4-way the incremental benefit is very less compared to the amount of power you are going to consume. Please note, if I have if I have content addressable memory, it takes lot of hardware, it consumes lot of power. Now it is not just one content addressable memory, for every line I have one content addressable memory. Are you able to follow? Right, yes or no, right. So I use these last two bits to index, then I do a complete content based search on that line, and so I have a content addressable memory on every horizontal line, right. So essentially the power consumption is going to be much higher. So now how do you decide, what would intuitively how will you try and answer this question? Yes.
Like say you said
this is an answer to my question. You are actually giving an answer to my question. I am asking you how many ways, how do you decide on the number of ways? Yes, it actually depends upon the cache usage pattern. Correct.
But can we really track how it's being used? Like
yeah, we can track. So we have something called architecture simulators, to which you run the program and it will tell you all the traces, like which memory location is accessed when, that it will give you. Now you can take just the memory traces. I do not really bother about, when I am looking at memory management, I do not bother about what application is running there. It may be some application to buy a buffalo, or it can be some hard-end ethical hacking thing, okay. I do not really care, it can be a great scientific computation. As far as I am concerned, I have the memory traces. Now I take these memory traces and put it into my simulator and find out how, if this is the cache size, what would be the cache hit, if it is the cache size, what would be the cache hit. So I can make that type of lot of things. I will come to that memory simulation also, I will try and cover that towards the end. So now, good, the first step is I have an infrastructure to find out for the programs that are interesting to me. I am making an architecture for some domain, right. For all the programs that are interesting to that domain, I know the memory traces. Memory traces means what are all the memory locations it will access, both instructions and data, that I have the trace. Now given this, how do you come out? Why do you think 4-way is still sufficient even for? So what will happen if I increase this? This is very short. So what will happen if I increase this? Come on, tell me, Kavya. What will happen if I make this more? Suppose I make this 8, right? Then this will become 3 bits, right? And this will become 3 bits, right? So what will happen? 0, the next fellow will be, this will go off. 0, next fellow will be 8, next fellow will be 16, next fellow will be 24, correct? So the distance between these addresses increase. That means what? Yeah. So for reasonable size program, normally you run program, everything would not be 4 GB, 100 GB, right? So everything would be small in size. So for reasonably, large programs, still the address spread will be so much that by the time your all the 4 ways get full, right? All the 4 ways get full, there will be no conflicts, right? So if I am looking at say some 512 MB cache, suppose I am looking at 512 MB, I am not, for example L3 cache, suppose I am able to get a 512 MB cache and it is 4-way also, correct? So 2 GB of cache itself I have on chip, suppose I have. Now what will happen, by the time that 4 ways get filled up, your program would have ended, meaning your size of the program will not be as large as filling up all the 4 ways of every line. Are you able to get this, right? So that is a very, very important thing. So what would happen is, first time when I am either fetching the instruction or fetching the data, it will be a miss, because it is there in the memory, it can't suddenly, its avatar cannot come in the cache. First time I am fetching from memory to the to the processor, it has to be a miss. So this is called a compulsory miss. Okay. So if you go to any processor company, they will ask, what are the different types of cache misses? First thing is a compulsory miss. It has to happen. First time I am accessing any instruction, first time I am accessing any data, that miss has to be there. So that is called compulsory miss. After that, so I brought in 8, I brought in 16, now 0 came, so 8 moved out. Now I have to again bring 8, right, because it has moved out. Once it has come in, then again it has moved out. This type of a miss is called conflict miss. This miss happened, though I had brought it once, this hit happened because there was a conflict. It was thrown out and again I had to bring in. Okay. So there are 2 types of cache misses, one is called a compulsory miss, another is called a conflict miss, right. Now what will happen is, as I keep increasing my size, I make this tall and I make this fat, right, then what happens, right, my compulsory misses are always going to be there, but my conflict miss will reduce, right, because the spread, the distance between the addresses are, the distance between the least address and the maximum address now become, now if I put a 4-way cache here, then the distance actually becomes 0 to 24, and I just double this size. While it was just 4 and only 2-way cache, then I had the distance was just 4 or distance was just 8. Now if something above 24 comes, then only this 0, 8, 16 and 24, one of them has to get replaced. Right. And if this is too large, 8 is a very small size or minuscule, minor, very minor size. So if this is quite large, then the number of conflict misses can essentially get minimized. Okay. So one of the questions is that what is it that you are trying to optimize? I am trying to minimize the number of conflict misses. Okay. So we are trying to optimize the number of conflict misses. Now can you give an algorithm? Let us just take 1-way cache. Okay. Let us just take a 1-way cache. Can you give me an algorithm which will be extremely benefited by the one. Before just going into that, now what we said was we are bringing one byte, right? 0 means I am bringing 0, 4 I am bringing 4, etc. But what we discussed in the previous class was I would love to bring k bytes at a time, right, and that is beneficial for me because I have the principle of locality. I have principle of both spatial locality and temporal locality. Instead of bringing one byte, I can bring k byte. By this, what I am trying to hide? I am trying to hide the latency tau that we are seeing on this side. Okay, I am reducing this tau, right? Otherwise, tau gets multiplied by k. So what will happen here is almost like paging. So instead of, so each line will not be one byte, it will be one block. So one block can be any, let us for sake of argument assume that this is going to be 256 bytes, right. So if I am bringing one location, I do not bring that location alone, I bring that block which contains that location. So what is 256 bytes? What is 256? 2 power 8. So if I take a 32-bit address space, how many cache blocks it will have? It will have 2 power 24 cache blocks, correct? Each of 256 bytes. So if I generate an address, say B31, B30, B29 to B8, B7, B6 to B0, this whole thing will give me the cache block, which block it belongs to, right? And okay, right? So it can tell me which block it belongs to, right? These are not necessary for me. So and within this I will now have a, so let us say I have 4 fellows here, so 0, 1, 2, 3, right. So this first, this 24 bytes will tell me which block it is going to belong to. Now B8 and B9 will tell me between the 0, 1, 2, 3 where it will fit. So I will go, and what will be my tag bit? B31 to B10 would be my tag bit. Okay, right? So if I just bloom one of this, zoom one of this, tag bit will be B31 to B10 will be tag, okay, and this will totally store 256 bytes. And we'll have one single valid bit and one single dirty bit, okay, to start with. Okay. So when you generate a since there are, when I generate a 32-bit address, the first 8 bits we are not bothered. This remaining, because each block is 256 bytes. Now I am looking at the remaining B31 to B10, B31 to B8. Within this B31 to B8, there are 4 locations in this cache. So I take the first 2 bits to find out which location will this, if at all this block is to be stored, which location will it be stored. So I take that first 2 bits. In those 2 bits, then I have B10 to B31. I go to that location and check if the tag corresponds to this, and the valid bit is 1. So now I will get a 256 bytes block. To this I input this 8 bit, last 8 bits into this 256 bytes to find the exact location, to access the exact location in the cache, right.
So what does the valid bit signify here?
Valid bit says, you see, otherwise anything is valid, no? Everything is 0 and 1, so everything is valid.
So it's valid for the first address, is it?
It is valid for the entire block. Oh, in this case, the valid bit and dirty bit is for the entire block. So even if you go and change one location in that block, and when it has to be replaced, the entire thing has to be copied.
So say we want to access some 10th instruction in this 256.
You will the cache would only see 256 bytes. If you go and change anything in that, the whole thing is I told you, right? If 1000 liters of milk, 1 drop of cobra poison, you will call it only poison. Okay. So you go and say this entire 256 bytes, you go and change one bit, gone. You go and even write, see it's already storing 2, just to make fun you write 2 again, still that fellow will say it's dirty and then, okay. Right? The moment you write into that location, the write access comes to the location, it becomes dirty. So when I replace, everything has to be written back. Okay. So let me just repeat once more so that you are very clear. We were dealing with 1 byte, now we are dealing with 256 bytes. Why I am dealing with 256 bytes? Because there is a latency hiding I am going to do, correct? I am going to hide latency, and it is very beneficial for me as of now, right? Because I have the notions of temporal and spatial locality that is given empirically proved on the programs. Okay. There is another thing that I am going to talk of little later, where without these type of block caches, the whole operating system will become defunct, meaning it becomes highly ineffective. I will tell about that later, but at least these 2 advantages we have. For that reason, what we do, if I want to bring one address, it is not there in the cache, I will bring the 256 bytes to which it is associated to. What do you mean by that association? A 32-bit address, the first 24 bits from the most significant bit will tell me which block it is. So from that, suppose I say this is a 4 location cache, I take the last 2 bits B8 and B9 to index into which location here, and the remaining things B10 to B31 I store it as a tag. Please note that for all the 256 addresses, this B10 to B31 will be the tag, B8 and B9 will be the index, correct, for all the 256 bytes, because this 24 bytes are fixed for those 256 bytes, correct, are you getting this? So the tag will be B10 to B31 and your B8 and B9 will tell you where to index, and then this is. Now this is a one-way direct mapped cache. Now if I make it 4 ways, same thing I will do. So I can store it, so I can add one more way here and the same thing. So now I am querying again that 22 bits, right, totally 8 bits goes off here, 2 bits go off here, 10, so 22 bits I query on each of these locations for the tag. I ask whether you are valid and is this tag there. If it says yes, then I use the last 8 bits to index into that location and basically find out. So this is how k-way set associative block cache will work. So this is called a block cache rather than a byte cache, because every time my unit of transfer, what this block, this cache looks at is minimum 256 bytes. It cannot resolve individual bytes in terms of this. Okay. So whenever I write into some location, essentially I am going and dirtying that block, and so if that location has to be replaced, then the entire thing has to be written and then a fresh thing has to come. Okay. Now how do you fix this? I am coming to a question. So how do you fix this 256 bytes? We fix this 256 bytes based on my performance requirement. If there is a cache miss, if I say I will put 1 MB block, right, then I will be bringing 1 MB of data here. Your temporal locality, again, no, anything more than a threshold, nectar also becomes poison. So like that, if you put 1 MB, right, so you will bring all these things, spatial locality will not exist for 1 MB. So I cannot be so far off this 1 MB, I can't remember, right. So I will not write a program with spatial temporal locality of 1 MB. maximum I will look at say some 10 instructions away or 20 instructions. So 256 bytes to or 512 bytes would be something much conceivable, or even say I can go up to Ks, 1K or 2K, but I can't say 1 MB and all. So that much memory the programmer doesn't have. Okay, so meaning in terms of visualizing a program. So 1 MB cache block will not work. So again this is all experimentation. So then, so what basically happens is there is an architectural simulator. In that simulator you run all your programs and find out so what are all the parameters now, how many ways I could have, what is the size of a block, these two are two parameters we have seen, and what is the height of the memory. So how long should it be, how fat should I be, and what is the block size. Okay, so 3 parameters already we have. So these 3 parameters we keep on juggling here and there and then come out with some optimal choice. And finally say if I put some 4, 5, 10 way and all, see, then your area also shoots up, your power also shoots up. So there is an implementation aspect of it, and also when I have a large set associative memory, my lookup also takes more time. So a performance also gets, when I make it more and more fat, your performance becomes slower, because now it's a set associative memory. So I have to, my performance essentially takes a toss, right. So now we understood cache modeling, right. So I have to look at area, I have to look at power, I have to look at performance, all from the circuit side, and again from an application side I should look at what would be the block size, what would be the number of ways, what should be the height of the memory, 3 parameters, so that I get best performance. So between these two I have to strike a balance. So already we have 6 parameters and each would have some 4 or 5 variants. So now imagine hundreds and thousands of paper we can generate just by looking at this policy, that policy, this policy. Okay, but that's the entire story about cache. So I will take 1 or 2 stories and tell you later also. Okay, now I am giving you this, let us just say 1 way, each is 256 bytes or whatever, 512 bytes or 1 KB, 1024 bytes. Can you tell me a program that will kill this, and can you tell me a program that will boost this? If at all I want to evaluate the performance, so I have put 1024 bytes 1 way. If I want to evaluate the performance of the cache, what sort of things will I start doing? What would be that program that can evaluate this? Loop, okay, because loop is the one, loop, because I am looking at locality, loop, and then loop, what will the loop do?
It depends on where exactly.
No, it depends on where, that I know. Now I am asking you, what is that thing which will make it depend on what you are saying? Okay, you are getting my question?
It's the location of where our.
How will you manage? Loop, she said, excellent, Kavya told loop. Now you say next. Function call inside loop. Function, see, I want this to be killed. I am killing an essential cache infrastructure. So it should be something huge.
I have an integer array.
Array. Why integer? So
Okay, it's not
floating point or anything. Array. Okay. Just array is enough. Array is a linear structure. Now I am saying it should kill, it should enhance. So what is a non-linear version of an array?
This.
Hey, version of an array. Linear 1 dimension matrix. Okay, correct? Are you able to get this? So I should have a loop acting on a matrix. Can you give me some examples? Matrix addition. Very good, man. So matrix addition, what will happen? Suppose, guys, carefully look into this. Okay, this is what we do in matrix addition, right. Now can you guess? Now, how is a matrix stored in the memory?
Linear.
Row major order, that's one way, column major order also. So what will happen? So this is first row, then second row, then third row, like that in the memory it will be stored. So here first row, first element is taken. So I am reading it row wise. So when I fetch the first element, 1024 elements will be fetched. So 1000 first element I fetch, it's a cache miss. Then I will have 1023 hits. Because along with the first element, 1024 elements will be fetched. Correct? Along with the first element, so into the cache, along with this first element, 1024 elements will be fetched. This is a block cache. So for every 1024 access, there will be only one cache miss, the remaining 1023 will be cache hit. And similarly for your B matrix, and similarly for your C matrix. Suppose I wrote it as for j equal to 1 to n, for I equal to 1 to n, Cij is equal to Aij plus Bij. That's all one. Both are equivalent programs. Correct? Both will add. Now what will happen? I will go and bring the first element, then that entire row will be brought. But I need the second column. I am accessed in this way. What will happen? Your matrix is accessed column wise. First element I will bring 1024 things inside, but none of them will be used. I want something else. Assuming this matrix is going to be a 10,000 by 10,000 matrix, which you see normally if you do weather modeling, you will see 10,000 by 10,000 matrix. First element I will bring, 1024 fellows I would have brought in, but no use. It's a miss, and that 1023 data is also no use, because the next fellow is going to be in the next column. So this is the first element, this is the second element, none of this I am going to access. You are getting this? Okay. By the time I come back and come to this second element, for all my luck this would have gone off. There is a huge matrix that I am trying to access, so something else would have come and rewritten on this. Okay. So what will happen is, for every I can fine tune the size of the matrix in such a way that for every access I am going to get a miss. While here for there is only one, every one miss I have 1023 hits. The same program, same functionality, it depends on who? It depends on the compiler, whether it is going to affect a column wise column major storage or a row major storage. If it does a column major storage and you access, if I do a column major storage and access it row wise, or if I do a row major storage and access it column wise, then I am going to have a big soup. Correct? So this is what we mean by a compiler optimization, impact of compiler on the architecture. Where does the compiler and architecture talk with each other? This is one more very interesting example. Are you able to follow? So we have talked about static instruction scheduling, dynamic instruction scheduling. We said compiler can be dud, compiler has to be extremely intelligent, right? In static instruction scheduling, compiler has to be intelligent. In dynamic instruction scheduling, compiler can be done, right? Okay. Now here, compiler also depends upon the architecture. So if you ask a question, why in a processor company like IBM, Intel, etc., why there is a compiler team, what are their works? Of course they have to write compiler which will translate, but more than translation there is something called architecture optimization. There are a lot of architecture optimization topics which you will learn in the compiler course. But one such thing, because we are talking about memory management here, is that the compiler should know, should allocate and drive the code like this, right, should allocate the memory in the same way as it is driving this. If arrays, the compiler by chance is storing the arrays as column wise, then when it is compiling these two, it has to swap this j and I to see that there is a better response. Are you able to understand? So how the compiler and the architecture, if they fight with each other, if they do not know about each other, then we may go into a toss, right. It may take years to execute this, but if I know each other and I want to work by, then what happens? Then it can do a good job. Okay. So this is one very interesting and important example about the interaction of a compiler with a architecture. We will take it forward. See, what I want is please revise these things, because this cache has so many things. Tomorrow I will talk about inclusive, exclusive cache, and slowly we will make this topic another 2-3 days. You need to have the continuity. Please understand what I have taught now.